Hi folks, welcome to the Fourier Zone. Today we're going to talk about a property that is so common, that we use so often, that you sometimes forget the kind of long winding path we took to get there. And it's called the convolution property of the Fourier transform, but it should almost be called the non-convolution property because it allows us to get, to associate the input and output of a linear time invariant system without having to go through the process of convolution. Okay, so let's derive that. So here's the idea. We know that we can, given a linear time invariant system with an impulse response h of t, we can find the input-output relationship between the input, say x of tau, through this convolution integral, right? What we'll show is that if we took the Fourier transforms of each of these, then the output can be obtained just by taking the product of the Fourier transform of x and the Fourier transform of the impulse response, or the transfer function. So instead of an integral, we can do everything we need to using just a product. Okay, and the proof is not very difficult, so let's go ahead and do that. So if I have y of omega is equal to minus infinity to infinity, y of t e to the minus j omega t dt, or I can write that as minus infinity to infinity and take this quantity and put that in here instead of y of t. And so this quantity is minus infinity to infinity, x of tau, h of t minus tau, d tau. And then this now is y of t, so that's y of t here. And then I put in e to the minus j omega t. And then dt. Right? Now what I'm going to do is I'm going to switch the order of integration. So I'll take d tau out and dt in. And you can pretty much do that most of the time with many of the functions that we see. There are times when you can't do that, but they're so not usual that we won't worry about it. So we take tau outside, and inside we're left with h of t minus tau. So functions of t, e to the minus j omega t dt, and then we have d tau on the outside. Okay, and now we're going to do a variable substitution. We'll take, define a variable, let's say u, to be equal to t minus tau. Then if I take the derivative of both sides, differential of both sides, du is equal to dt, because as far as this integral here is concerned, tau is a constant. So when I take the differential, this will just go to 0 and I'll get du is equal to dt. And of course, t will be equal to u plus tau. So plugging all of that in here, I get this is equal to minus infinity to infinity, x of tau, minus infinity to infinity, h of u, e to the minus j omega, and now instead of t I have u plus tau, so I'll write u plus tau, and instead of dt I'll have du, and then d tau. Right? So now let's just split this one up, and I can write this as, again, minus infinity to infinity, x of tau, integral minus infinity to infinity, h of u, and then I can write this thing as e to the minus j omega u, e to the minus j omega tau, and then I have the inner integral du and the outer integral d tau. So now what I'm going to do is e to the minus j omega tau. Tau is not a function of u, so I can take this out of this integral, and I get minus infinity to infinity, x of tau. I'll take that e to the minus j omega tau and put it here. And then here I have integral from minus infinity to infinity, h of u, e to the minus j omega u du, and then d tau. Right? But this thing here, this integral here is just h of omega. Right? And because it's just h of omega, I can take it outside of this integral. And then what I'll be left with is this integral, and that gives us x of omega. So we get, finally, remember that we started out with y of omega. So y of omega is equal to x of omega times h of omega. So in a lot of applications, what we're looking at is h of omega is going to be some kind of a filter. So this will be the transfer function of the filter. X will be our input. And we'll want to see what the effect of that filter is on the output. Or sometimes we know what the input looks like. We know what we want the output to look like. And what we want is we want to be able to find the transfer function of the filter that gives us what we want. So given that y of omega is equal to x of omega times h of omega, if I know what the desired y of omega is and x of omega is, then I can find the filter transfer function by just dividing both sides by x of omega. And so I'll get the output over the input. Right, so that's really nice. And this is something that you will use many, many, many times in your career. But remember that it actually came from the convolution integral, right? So we started out from the convolution integral and we ended up with this equation here. Okay. Filters. So we're not going to be designing filters in this class, but just for a moment, let's just talk about it just a little bit. So a lot of times we use this brick wall filter. Let's say h of omega is equal to 1 when omega is less than some w and 0 otherwise, right? So we've done this a few times, and especially in the post quizzes, you've seen filters of this sort. Okay, and we've mentioned most of the time that when you have this kind of a filter is not realistic. And what I want to show you is why it's not realistic. And in order to show you, what I'll do is I'll take the inverse Fourier transform of this to come up with the impulse response. And then using our knowledge of the impulse response, we can see why this is not a realistic filter. So h of t then is the inverse Fourier transform of h of omega, which is 1 over 2 pi integral from minus infinity to infinity, h of omega, e to the j omega t, and I better get this right, d omega. So I'm left with t in the end. And so if I plug this in here, h of omega is just 1 for omega between minus w and w, and is 0 everywhere else. So the integral from minus infinity to infinity reduces to the integral from minus w to w. And in this interval, h of omega is just 1. So I just have e to the j omega t d omega. And so this is equal to 1 over 2 pi. Remember, the integral is with respect to omega. So 1 over 2 pi jt e to the j omega t evaluated between minus w and plus w, or that's 1 over 2 pi jt, and plugging in these values I get e to the j wt minus e, because I'm plugging in 4 omega minus e to the minus j wt. Okay, or I can take this 2j inside. So this is 1 over pi t e to the j Wt minus e to the minus j Wt over 2j. And this we know because of Euler that this is just sine of Wt. So we have this is sine of Wt over pi t. This is a form we've seen before. And so if we plot this out, we'll get this very familiar form. By the way, this thing is often called a sinc function. So we'll get this nice sinc function. Okay, everything's peachy up to here, except now notice that this is the impulse response, right? The impulse is occurring at this point, and this is the filter responding to the impulse occurring at this point. This is the past, this is the future, so that means that the system is responding prior to the impulse, prior to the input showing up. In fact, it's responding, this goes all the way to minus infinity, so it's responding infinitely far ahead of when the input is going to occur. And that makes this not realizable. It's having this thing go off to minus infinity means that this thing is not going to be realizable. That's why this is a brick wall filter, is not something that you can get, right? What can you get? Well, there are a number of different filters types, and we won't go into that, but there is Butterworth filters. And this has been, people have been doing this for ages and ages and ages. So there's Chebyshev filters. There are multiple kinds of Chebyshev filters, type 1, type 2. There's elliptical filters, and each one of them has its own positives and negatives. Butterworth filter is the one that is kind of nice. I mean, it has, a reasonably flat passband, but then it doesn't go down the way this one does. It doesn't have that sharp transition, and it kind of rolls off. And depending on the order of the filter, you can make it higher or lower order filter. The higher the order of the filter, the more complex your system is going to be, but the sharper this transition you can get. But still, you're going to get some kind of a roll-off. And I put a circuit diagram for I think a third order Butterworth filter into the notes, so you can take a look. I mean, it's not very difficult. It's just RC circuits with an op amp, and there are three. It's a third order filter, so you get 3 capacitors in different places, and you can build it if you want. So that's what a Butterworth filter will do. A Chebyshev filter does have a sharp transition. So this is, I'm just drawing the magnitude of the filters. So a Chebyshev filter will give you a sharp transition, but you have to pay for it. And the way you pay for it is you get the sharp transition, but then like in the type 2 Chebyshev filter, you get ripples in the stop band. So it doesn't completely stop the frequencies outside of your region of interest. You still get these ripples. Or you can try and say, okay, I don't want ripples in the stop band. I really want to kill whatever signal is out here. And you can get a type 1 filter, and a type 1 filter has ripples in the pass band. And it has a very nice sharp roll-off, and it blocks off the components in the stop band. So this band here, the band of frequencies that is going to pass is called the pass band, and the band of frequencies that are going to be stopped is called the stop band. Okay, well, this is not very difficult. Passive filters are really simple to build because there are all kinds of nice little algorithms that are out there that allow you to build them, and they're also nice little circuits that you can modularly put together to build different kinds of these filters. Okay, but that's not part of what we're going to do. Okay, so let's take a look at using this to find the response of our nice little simple filter that we had, the RC filter. If you remember, the response of the RC filter was given by just an exponential. So the impulse response of the RC filter was equal to alpha e to the minus alpha t u of t, right? Where alpha was just equal to 1 over RC. So that was my RC filter. And what I want to do is go through a couple of different inputs for this and then just compare what you would get from the input from the convolution integral and what you get with the transform method. So the Fourier transform of this is going to be integral from minus infinity to infinity, alpha e to the minus alpha t, e to the minus j omega t dt, which is equal to alpha times integral from minus infinity to infinity, and there's a u of t here. So the u of t will make this 0. So it will be the integral from 0 to t of e to the minus alpha plus j omega t dt. And that gives us minus alpha over alpha plus j omega e to the minus alpha plus j omega t evaluated between 0 and infinity. And if you remember, we kind of hammered this last time. At infinity, this thing is just going to go to 0. And when we plug in 0, this is equal to 1. So this is just equal to alpha over alpha plus j omega. Right, so that's the transfer function of my RC filter. So let's take a very simple RC filter. Let's take alpha to be equal to 1 so that my impulse response is e to the minus t u of t. And let's look at the output for a couple of cases. So let's suppose x of t was going to be equal to e to the minus 2t u of t. Right, so we get, if you do this the convolution way, let's suppose this is h, or this is x of tau, and then you have h of t minus tau, and that will, if t is less than 0, it'll be back here, and if it's t is greater than 0, it'll be up here, right? So if t is less than 0, the output for this given input is just equal to 0. And when t is greater than 0, then this will be like this, where this point is t. And so I'll get an integral from 0 to t of x of tau, h of t minus tau. So x of tau is e to the minus 2 tau, and h of t minus tau is e to the minus t minus tau d tau. And you can work this out. This is going to be e to the minus t. If I just add these exponents together, I'll get e to the minus t minus tau, and I can take that e to the minus t outside. We've done this before, so that's why I'm just kind of hurrying through this. And this works out to be e to the minus t 1 minus e to the minus t u of t. So for t greater than 0, so I don't have to write that down. Or that's equal to, when I multiply this out, this is just e to the minus t minus e to the minus 2t, right? So that's what we get with the convolution. Now, what will we get if I multiply the Fourier transforms with these? Well, the Fourier transform of this, we just saw, was just 1 over 1 plus j omega. And using the same argument, I can find this x of omega is equal to 1 over 2 plus j omega. So basically what we have is that if I have e to the minus at u of t, and I take the Fourier transform of that, that's going to be 1 over a plus j omega. Right? And I'm assuming that a is positive so that, this thing is stable. Okay, so that's h of omega, that's x of omega, y of omega. I can write as a product of the two. So it's this times this. So that's 1 over 1 plus j omega times 2 plus j omega. Now here is something that you kind of have to remember from way back from your calculus. This is something that we will be using over and over again, and that is we'll have things like this, rational polynomials like this, where we can factor out the denominator, and you have to be able to write this in terms of each of the factors in the denominator, and that's what you do with partial fraction expansion. And different people have learned partial fraction expansion in different ways. Whichever way you've learned partial fraction expansion, use that. But do go back and look at how to do partial fraction expansions. That's going to be important in many, 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 many different applications from now on. So partial fraction expansions is one thing you really do need to know. So go back and look at it again. Or if you remember it, wonderful. Okay, so I used partial fraction expansion here, and what I got was, let me write it out, this was equal to 1 over 1 plus j omega minus 1 over 2 plus j omega. Okay, and now I can find what y of t is directly, because I know 1 over 1 plus j omega is the Fourier transform of e to the minus t u of t. And the Fourier transform is unique. So you have e to the minus t u of t, and its Fourier transform is 1 over 1 plus j omega. Then the inverse Fourier transform of 1 over 1 plus j omega has to be e to the minus t u of t. Right? So y of t is equal to, and I'm going to use linearity. I'll take the inverse Fourier transform of this, inverse Fourier transform of this, and subtract them. So I get e to the minus t u of t minus e to the minus 2t u of t, or I can put these together, and I get e to the minus t minus e to the minus 2t u of t, which is exactly what I had before, except that I could do it very simply. I didn't have to go through convolutions. I just went through in 2 steps to get the output. So that's really kind of nice. Okay, let's look at one more example, and that is going to be a bit more complicated, but it's an important example, so let's do it. And that's, I'm going to stay with the same impulse response, but I'll change the input to the step function. We did this before when we were looking at convolutions, and if you remember, having a step function as the input, all you get at the output is that the capacitor charges up to whatever the value of the input is. In this case, the input has a value of 1, so the capacitor will just charge up to 1. Okay, but we have a slight problem here, and so I want to go through that and show you what the problem is and what the solution to that problem is. So the problem is this. If you remember the Dirichlet conditions, the first Dirichlet condition, and these are the conditions that are required for the Fourier integral to exist. The first Dirichlet condition was that if I have some x of t, then the integral from minus infinity to infinity of the absolute value of x of t has to be less than infinity, has to be finite. Now the unit step function is this, like and it goes on up to infinity. And if I take the area under here, which is what this integral is, then this area is going to go to infinity. So u of t clearly violates the first Dirichlet condition. So I can't use the Fourier integral to find the Fourier transform of the step function. But the step function is an important thing, so we're going to use it over and over again. So I kind of need to figure out a way to deal with this. And the way I will deal with this is by using another property of the Fourier transforms, which is called the differentiation property. Okay, and the differentiation property says this. It says that if x of t has a Fourier transform x of omega, then the Fourier transform of the derivative of x of t is equal to j omega times x of omega. And I'm going to show this. It's really easy to derive, so we'll go ahead and derive this. Okay. So how do we do that? Well, we start. Okay, there's one thing though. I need to make sure. Remember that the relationship between x of t and its Fourier transform is, well, one of the ways you can relate them is through this integral, and the other one is through the forward integral. So if I have this, e to the j omega t, and this will be d omega. This is a way of relating these two. So if I had something else, something here, if you ever see something here, and on this side you see 1 over 2 pi minus infinity to infinity, something else, e to the j omega t, d omega. If you see this relationship, then what this says is that the Fourier transform of whatever this is equal to whatever this is. Okay. Kind of have to remember that, right? Okay. So now let's go back and do our derivation. So x of t is equal to 1 over 2 pi integral from minus infinity to infinity of x of omega e to the j omega t d omega. Now I can take the derivative of both sides. So on this side I have d by dt x of t, and this side I have d by dt of this thing, 1 over 2 pi integral from minus infinity to infinity x of omega e to the j omega t d omega. Now what I'm going to do is I'll switch the order of integration and differentiation. I can do that whenever I don't end up with a situation where something becomes infinity. If this integral integrated out to infinity, I'd have a slight problem here. But as long as it doesn't, I can do that. So I can change this to 1 over 2 pi, the integral from minus infinity to infinity, d by dt, x of omega e to the j omega t, d omega. And now the derivative I'm taking is of this, and it's with respect to t. This has nothing in here that has anything to do with t, so I can kind of take this out of the derivative. And the derivative of e to the j omega t with respect to t is just j omega e to the j omega t. So this is 1 over 2 pi integral from minus infinity to infinity j omega t, j omega, no t's, because I took the derivative with respect to t, x of omega e to the j omega t d omega. Right? This is this. This is this, right? So the Fourier transform then of d by dt x of t is equal to j omega x of omega. Okay, so that's the differentiation property. Now what I'm going to do is I'm going to kind of flip this around. So I'll show you how you can use the derivative, the Fourier transform of the derivative, to come up with the Fourier transform of the function itself. Okay, so I'll change things around a little bit. So let me rewrite this. So this is Fourier transform of d by dt, x of t. is equal to j omega, and x of omega is just the Fourier transform of x of t. Right? So what I can do is I can switch sides, and I can say the Fourier transform of x of t then, and is equal to 1 over j omega times the Fourier transform of d by dt x of t. Okay, so I can find the Fourier transform of a function by finding the Fourier transform of its derivative and dividing by j omega. There is only one thing you have to be really, really careful of, is that x of t should not have a dc value in there. Because when I take the derivative, if there is a constant term in here, that constant term is going to go to 0 and will disappear. So I need to be able to remember that. Otherwise, what I will get is, if I have some function of t plus 2 and some other function of t minus 1,000, both of them would have exactly the same, because both of them will have the same derivative, because this term will always go to 0 when I take the derivative. It'll seem like both of these terms have the same Fourier transform, which is not true. Okay, so I have to make sure that if I'm using this method to find the Fourier transform of something, I need to make sure that the function has 0 DC value. Now there we run into a problem, because remember what we're trying to do. We want to find the Fourier transform of the unit step. But the unit step is this, and it clearly has a DC value. The DC value is the average value, and the DC value in this case is a half. So I really can't use this directly. However, I can do this. So here's the signum function, all right, which is 1 for t greater than 0 and minus 1 for t less than 0. Let's take half of that. So let's take half of signum of t. So that's going to be a half here and a half here. Half and minus a half. And then if I add to it the constant value of a half, then what's going to happen? For t less than 0, I'll get plus a half, plus minus a half, and that'll give me 0. For the positive, for t greater than 0, I have plus a half, that'll give me 1. So what I can see is that u of t is equal to signum of t, a half signum of t, plus a half. Right, so that'll give me my unit step. And the nice thing now is that this signum of t has an average value of 0. It's plus a half of the time, and minus a half the other half of the time. So the average value is going to be 0. Right? So then I can use this nice little trick where I can find the Fourier transform of this half signum t by looking at the Fourier transform of its derivative and then just dividing it by j omega. Okay, and then I can use linearity. I can find the Fourier transform of this. I can find the Fourier transform of this, and then I can add them both together, and that'll give me the Fourier transform of phi of t. Okay, so what's the derivative of this? Well, think about it. This is the rate of change, right? So the derivative of this is 0 everywhere except at 0, where you have this jump, in this case, of 1. Right? So the derivative of this thing is just an infinite. So it's 0 everywhere except here with infinity, and that's just the delta function. Right? And this has a height of 1. So d by dt of a half signum of t is equal to delta of t. Okay, so now the Fourier transform of a half signum of t using my thing here is going to be 1 over j omega, the Fourier transform of the derivative, which is just delta of t. And the Fourier transform of the derivative is really easy, because it's just minus infinity to infinity, delta of t, e to the minus j omega t dt. right? And I use the shifting property of the delta function, which says that the result of this integral is you take the variable of integration and you just replace it with whatever value makes this argument go to 0. In this case, t equals 0 makes this argument go to 0, so I plug that in here, and this is equal to then 1 over j omega e to the power 0, which is just equal to 1 over j omega. Right? So the Fourier transform of a half signum of t is just 1 over j omega. And now I have to figure out what the Fourier transform of a half is. Well, for that, you remember that whenever you have a constant either in the time domain or the frequency domain. In the other domain, you have to have a delta function. That's the only way that you're going to get a constant in the time domain. If it's constant in the time domain, you'll get a delta function in the frequency domain. If it's constant in the frequency domain, you'll get a delta function in the time domain. Okay, so you can see this. If I take, 1 over 2 pi, let's take the inverse Fourier transform of a delta function. So the Fourier inverse of delta of omega is equal to 1 over 2 pi integral from minus infinity to infinity, delta of omega e to the j omega t d omega. And again, I use the shifting property of the delta function. So this is going to be 1 over 2 pi times e to the power 0, which is 1 over 2 pi. Okay, but I don't want 1 over 2 pi. I want 1 over 2. And so then that means that the Fourier inverse, in order to get 1 over 2 here, what I need to do is multiply both sides by pi. So if I multiply this side by pi, then that'll multiply this side by pi, and that'll multiply this by pi, and that'll multiply this by pi, and I'll get 1 over 2. So the Fourier transform of 1 over 2 is pi delta omega. Okay, so now I have everything I need. So the Fourier transform of, let's change pages. So the Fourier transform of the unit step now is just 1 over j omega plus pi delta of omega. Okay, and now I can go back and I can do my, this was my input. So this is x of omega. And remember that h of omega was just equal to 1 over 1 plus j omega. So y of omega will be equal to this whole thing, 1 over j omega plus pi delta of omega times 1 over 1 plus j omega. And then that's just 1 over j omega times 1 plus j omega plus pi delta of omega times 1 over 1 plus j omega. So I'm multiplying these two functions. This function here only has a value at omega equals 0, so I can just set omega to be equal to 0, right? And that gets rid of this entire factor. And so I've got 1 over j omega times 1 plus j omega, and I have pi of delta omega here. So now what I need to do is take this one, and again, I break it up into its factors using partial fraction expansion. And if I do that, I get, this is 1 over j omega minus 1 over 1 plus j omega, and then I have plus pi delta omega from here. Right? But this thing here, these two terms, that's just the unit step. That's just the Fourier transform of the unit step. So when I look at y of t, I take the inverse transform of this. These two terms give me u of t, and this term is e to the minus t u of t. Or I can put these together, and that's 1 minus e to the minus t u of t. So this was, we took a long time doing this, but mainly because we needed to find the Fourier transform of U of t. And that's an important function for us. So we did need to spend a little bit of time trying to find the Fourier transform of that. But once now we have it, we have it forever. We never have to figure it out again. And life becomes really kind of simple. Okay, so what have we done? First, we have said that the Fourier transform of a convolution in the time domain, let's see, x of t convolved with h of t is equal to the multiplication in the Fourier domain. Right? So if I have a convolution in the time domain, I can replace that with a multiplication in the Fourier domain, and that'll make life really, really simple for us. Okay, we talked a little bit about filters. I kind of want you to at least know about them. I don't know that we'll do a whole lot with them right now, but you should at least know what they are and why you can't have that really nice ideal case. Okay, so that's one. And then we said we had looked at the differentiation property, which was that the Fourier transform of the derivative of x of t is equal to j omega times x of omega. And from here, we figured out how to find the Fourier transform of something which doesn't satisfy the Dirichlet conditions, and therefore you can't use the Fourier integral to find the Fourier transform of that, right? So we found the Fourier transform to be equal to 1 over j omega plus pi delta of omega, and that's it. This is kind of important, this one, because of the convolution property. You have to understand why we can multiply things in the Fourier domain when we have to go through all that hassle of doing convolutions in the time domain. And it's very nice because now you don't have to worry about convolution. Whenever you see a convolution, you can always go over to the frequency, to the other domain. It'll turn out that, convolution in the time domain results in multiplication in the frequency domain. It'll turn out the other way also works. If you have convolution in the frequency domain, that'll turn out to be multiplication in the time domain. So whenever you see an operation of either convolution or multiplication, and whichever one is easier to do, that's the one you'll use. Okay, so I'll leave you with that.